Hi, my name is Talia. I'm an incoming second-year student at UCSD studying chemistry. This YouTube channel is for anyone and everyone who may need some extra help brushing up on chemistry topics or learning them for the first time. Today I'm going to be continuing on my thermodynamics series by going over kind of an introduction to heat of reaction problems, and in following weeks I will explain different methods to figuring out the heat of reactions or the enthalpy. So if you need some help with that, I hope you will join me and continue watching. Without further ado, let's get started. Okay, so like I said, this video is going to cover heat of reaction basics. So just to get started, chemical equations that we have seen are sometimes written with a heat term either on the reactant side or on the product side or separately from the entire equation, and that is called the enthalpy or the heat of the reaction. That heat term, its sign or where it is placed in the chemical equation, tells you if the reaction is endothermic or exothermic. If you don't know those terms, have no fear, we're going to go over them in the following slide. So when you're given the heat for an entire reaction, usually given in units of kilojoules per mole, you can convert it into the heat required or released based on a certain amount of a reactant or product used in the reaction. Very similar to stoichiometry problems we've done in the past. If you would like some review on stoichiometry, I have a video on that as well. So the basic calculation for heat or enthalpy that we're going to be using in this video is that the delta H is the heat of the products minus the heat of the reactants. When we learn other methods for calculating enthalpy, the calculations will change slightly, but this is what we're going to be using today. So endothermic versus exothermic, what's the difference? These two words are used a lot. So I've included graphs. We're first going to go over endothermic reactions. So in endothermic reactions, the products have more heat than the reactants, which means heat is absorbed or heat is required for the reaction to happen. Therefore, the heat term is written as a reactant in the chemical equation because you need heat to get it going. An alternative way to write the heat term is just by writing it separately from the reaction, but writing it as a positive number. Because, like the equation from the previous slide, if you look at the heat of the products minus the heat of the reactants, it's a positive value. Conversely, we have an exothermic reaction where heat is lost or released as a reaction occurs, and then this means that the products have less heat than the reactants, and therefore delta H is negative. So there are two ways you can demonstrate this in the chemical equation. Option one is by writing the heat term as a product in your reaction because heat is released, it's a product. But you can also write it separately from the chemical equation with a negative sign, because if you do the delta H of the products minus the delta H of the reactants, you'll get a negative number. And you might be wondering why I'm using heat instead of energy, which is the y-axis on these graphs. Heat is a form of energy. So with that information, we're going to get into an example problem. So if we consider the following reaction.
The reaction is 2 moles of carbon plus 3 moles of hydrogen gas yields 1 mole of ethane and 83.8 kilojoules of heat per mole of the reaction.
So if we have 2.8 grams of carbon and 0.722 grams of hydrogen gas, which reactant is limiting and which is excess, and how much heat is produced by the reaction? So some things to remember before we get into it. We have heat as a product, which means that this is an exothermic reaction, and 83.8 kilojoules per mole, which is negative if we were to write it separately, means that in 1 mole of the reaction, the 83.8 kilojoules of heat is released.
But that also means that there are 83.8 kilojoules of heat released for 2 moles of carbon or 3 moles of hydrogen gas or 1 mole of ethane.
So I took the coefficients in front of each compound and the heat term and made a ratio because the units of heat are kilojoules per mole. So that per mole can be applied to per mole of each reactant product. So now let's get started. The first part of this problem is a basic limiting and excess problem. Our first step is we are going to take the mass of carbon and mass of hydrogen and convert it all the way to moles by dividing by the molar mass, and don't forget to divide by the molar mass of H2 because hydrogen is diatomic. And then now we are going to divide by the coefficients in front of the compounds. So we are going to divide the moles of carbon by 2 and the moles of hydrogen by 3. And then we notice that the moles of hydrogen are smaller, and therefore Hydrogen is the limiting reactant and carbon is the excess reactant. We can take our moles of hydrogen and use that conversion fraction I showed a couple slides ago and figure out how much heat is produced by the reaction. So if I have 0.33 moles of hydrogen gas and I multiply it by negative 83.8 kilojoules per 3 moles of hydrogen gas, because that is how much heat is released in one reaction, which utilizes 3 moles of hydrogen gas, I will get that there are negative 10.7 kilojoules of heat in the reaction, which means that there are 10.7 kilojoules of heat released because this is an exothermic reaction. So yes, technically the heat is negative, but because the question is asking how much heat is produced, which is analogous to release, we can say that 10.7 kilojoules of heat are released. I hope you enjoyed this video on basic heat of reaction problems. If you have any questions, feel free to leave them in the comment section below. Next week, I'm going to be talking about another method to calculate heat of reaction using bond energy. And that is going to be slightly more complicated, but using similar principles that I went over in this video. So feel free to join me if you need some help with that topic. I hope you enjoyed the video and good luck with learning chemistry.